The single grain of common table salt resting on the edge of a kitchen knife represents one of the most successful chemical ceasefires in the history of the universe. Half of this harmless, translucent crystal is composed of a substance so physically aggressive and thermodynamically unstable that it cannot exist in its pure form for more than a few seconds in a typical human environment without triggering a violent release of energy. This substance is sodium, the 11th element of the periodic table, and it functions as a silver-white psychopath of the material world, a metal that defies almost every sensory expectation and engineering standard associated with the term. To understand the modern world, one must understand how human ingenuity learned to cage this volatile element, utilizing its explosive potential to drive our biological nervous systems and illuminate the corridors of our cities. This deep dive into the hidden mechanics of the elements is part of an ongoing investigation into the building blocks of reality. Subscribing to the channel and contributing a perspective in the comments ensures that these detailed explorations into the fabric of our world continue to reach those who seek a sophisticated understanding of the physical universe. The physical reality of pure sodium is a radical departure from the rigid, unyielding nature of iron or copper. If a block of high-purity sodium were placed before an observer, the initial impression would not be one of structural metal, but rather of a dense, chilled slab of mineral-rich butter or a heavy block of industrial wax. Sodium is remarkably light, possessing a density of approximately 0.97 grams per cubic centimeter, which means it is slightly less dense than H2O. This lightness is a direct consequence of its atomic configuration. Within its crystalline lattice, the sodium atoms are relatively far apart, creating a structure that is airy in an engineering sense, despite its metallic classification. The most startling physical characteristic of this element is its extreme softness. While most metals require massive industrial shears or intense heat to be reshaped, sodium can be sliced with a common steel kitchen knife with minimal resistance. This process reveals the true nature of the element. As the blade passes through the dull, grayish exterior crust, which is a layer of oxide and hydroxide formed by contact with the air, it exposes a brilliant, mirror-like surface. For a few brief moments, the fresh cut of sodium possesses a silver-white luster that reflects nearly 100% of incoming light, appearing as an almost otherworldly, liquid-like mirror. However, this perfection is an unstable state. Within seconds, the mirror begins to fog and tarnish, turning back into a dull, leaden grey as the surface atoms engage in a frantic chemical reaction with the oxygen and moisture in the atmosphere. This is not a choice made by the metal, but a rigorous thermodynamic necessity. The sodium atom is in a state of high potential energy, much like a tightly coiled mechanical spring held in place by a fragile latch, and it will seize any opportunity to shed that energy and reach a more stable configuration. This chemical restlessness is what defines sodium as a nervous element. At the atomic level, sodium possesses 11 protons and 11 electrons. 10 of these electrons are arranged in stable inner shells, but the 11th electron sits alone in the outermost shell. In the language of atomic physics, this valence electron is a burden. Because it is shielded from the positive pull of the nucleus by the inner electrons and is located relatively far away from the center of the atom, it is held with very little force. The sodium atom exists in a state of constant readiness to give away this electron to any passing atom that can accept it. This drive is so powerful that sodium is never found in its metallic state in nature. Every gram of sodium on Earth is naturally locked in a chemical marriage, typically with chlorine or oxygen, where it has already surrendered its troublesome outer electron to achieve the stability of a full shell. The interaction between pure sodium and H2O is the most famous demonstration of this electrochemical aggression. When a small fragment of the metal is placed in water, it does not simply dissolve or sink. It initiates a rapid exothermic causal chain. The sodium atoms on the surface immediately react with the water molecules, displacing hydrogen and forming sodium hydroxide. This process generates an immense amount of heat in a microscopic area. Because sodium has a relatively low melting point of only 208 degrees Fahrenheit, the heat of the reaction is sufficient to melt the metal fragment almost instantly. The sodium transforms into a shimmering liquid sphere that skims across the surface of the water, propelled by high-pressure jets of escaping hydrogen gas. This is an exercise in kinetic and thermal physics. As the sphere dances, it acts like a miniature hovering craft, riding on a cushion of steam and gas. If the temperature of the localized environment reaches the ignition point of approximately 240 degrees Fahrenheit, the hydrogen gas ignites. The result is a violent hysteria of sparks and a characteristic yellow-orange flame, often culminating in a sharp explosion as the internal pressure of the molten sphere overcomes the surface tension. To an observer, this looks like the metal hates the water, but to an engineer, it is simply a high-speed redistribution of electrons and a release of binding energy that was forged in the heart of a star. Because of this extreme reactivity with the atmosphere, the management of sodium requires specialized containment protocols. In a laboratory or industrial warehouse, the psychopath must be kept in permanent isolation. This is achieved by submerging the metal in a bath of hydrocarbon oil, such as mineral oil or kerosene. The oil functions as a physical and chemical seal, excluding both oxygen and H2O vapor. Because the oil is less dense than the metal, but possesses a high enough viscosity to prevent circulation, it ensures that the sodium remains in a state of suspended animation. Without this protective layer, the humidity in a standard room at 70 degrees Fahrenheit would be enough to cause the surface of the metal to liquefy and eventually ignite, turning an office or a storage room into a chemical furnace. The great paradox of sodium is the contrast between this metallic psychopath and the pacified version we encounter in our daily lives. This transition occurs through the formation of the ionic bond. Chlorine is an element that is the perfect mirror image of sodium's needs. While sodium has 1 electron too many, chlorine has 7 electrons in its outer shell and is desperate for an 8th to complete its set. When these two elements meet, the reaction is not a struggle, but a total energetic reconciliation. The sodium atom physically transfers its lone electron to the chlorine atom. In this exchange, both atoms become ions, one positively charged, one negatively charged, and they lock together into a rigid cubic lattice held by immense electrostatic forces. This resulting substance, sodium chloride, NaCl, is the ultimate expression of stability. The quote underscore 11 underscore energy of the sodium and the aggressive quote 12 of the chlorine have been entirely neutralized. The salt crystal is so stable that it can remain unchanged for hundreds of millions of years in a subterranean deposit. It possesses a melting point of 474 degrees Fahrenheit, a temperature 7 times higher than the melting point of the pure metal. We can safely handle it, eat it, and store it in our kitchens precisely because the quote 13 potential of the sodium has already been quote 14 during the formation of the bond. To look at a salt shaker or a block of pure sodium is to see 2 different chapters of the same atomic story. One is a state of high potential chaos, a material that demands isolation and absolute respect for its thermodynamic boundaries. The other is a state of satisfied order, a material that provides the essential saline environment for biological life. Sodium is a substance of extremes. a metal that provides the __15__ for our technology and our biology, but only after it has been tamed by the geometry of the crystal. It is the silver-white ghost of the periodic table, hiding its aggressive soul behind a mask of ordinary white grains, reminding us that the most essential components of our existence are often those that were the hardest for nature to stabilize. Every slice of the knife into that __16__ metal is a reminder of the raw, unrefined energy that the universe uses to build the complexity of a world that, for the most part, appears peaceful and still. The presence of sodium in the Earth's crust and the depths of the global ocean is the final result of a high-stakes nuclear ledger that operates only in the terminal stages of the most massive stars in the galaxy. While the universe began with the simple, primordial abundance of hydrogen and helium, the creation of an element as complex as sodium required a sequence of thermal and gravitational pressures that dwarf the energy output of 1 trillion suns. To understand the biography of a single atom of the 11th element is to look back to a period of cosmic history where matter was subjected to a hierarchical ladder of fusion, moving from the steady burn of youth to the frantic high-temperature desperation of stellar middle age. Sodium is a material forged in the neon burning phase of a star, possessing at least 8 times the mass of the solar system's center, a process that occurs only when the celestial furnace has exhausted its primary fuels and is beginning to consume its own internal ash. The production of sodium-23, the only stable isotope of the element found in nature, is a masterclass in nuclear efficiency. Inside these gargantuan stars, once the hydrogen and helium have been converted into carbon and oxygen, the core undergoes a massive gravitational contraction. This contraction increases the internal pressure to a point where the temperature reaches approximately 1.2 billion degrees Fahrenheit. At this extreme thermal threshold, the star enters the neon burning phase. This is not a slow process. It is a rapid-fire sequence of subatomic transformations. To explain this on the fingers, the star acts as a high-pressure kitchen where the ingredients are constantly being forced together by the weight of the overhead building. Under this intense heat, neon atoms begin to break apart, releasing alpha particles, which are essentially helium nuclei. These free-floating alpha particles then strike other neon atoms, initiating a capture process that transforms the neon into magnesium. However, through a secondary pathway involving the capture of free protons, the 10th element is pushed one step further to become sodium. This phase of a star's life is remarkably brief, often lasting for only a few years, a mere blink of an eye in a life cycle spanning millions of years. Despite its brevity, the output is prolific, saturating the star's interior with sodium ions. However, the sodium remains a prisoner of the star's gravity until the final act of the stellar drama, the supernova. When the star eventually reaches the ion stage and its internal pressure can no longer resist the inward pull of gravity, it undergoes a catastrophic core collapse. The outer layers of the star are ejected into the interstellar medium at a significant fraction of the speed of light. This event acts as a celestial shotgun, spraying the newly forged sodium, oxygen, and neon into the void as microscopic dust and gas. The sodium found on Earth today is essentially the __17__ from these ancient explosions, drifting through space for eons as part of massive, cold clouds of molecular gas. Approximately 4.6 billion years ago, a segment of one of these enriched clouds began to collapse under its own gravity to form the solar system. As the solar nebula spun and flattened into a disk, the distribution of elements was dictated by the __18__, a temperature boundary that determined which materials could remain solid and which would stay as gases. Sodium, despite being a metal, is highly reactive and was among the first substances to bond with the surrounding oxygen and silica. It did not remain a solitary traveler in the gas clouds. It immediately sought out partners to form the rocky minerals that would eventually constitute the terrestrial planets. When the Earth began to coalesce from a roiling ball of molten rock and metal, the behavior of sodium was governed by its specific chemical preference known as lithophilia, or a love for stone. According to the laws of planetary differentiation, a process often described as the __19__, the heaviest materials should have migrated to the center of the Earth. Just as a lead weight sinks through H2O to the bottom of a bucket, dense elements like gold, platinum, and iron descended 1,800 miles beneath the surface to form the planet's core. By the logic of mass alone, sodium should have followed this downward migration. However, sodium's atomic structure, that single, loosely bound outer electron, prevented it from joining the iron abyss. Sodium possessed a far greater thermodynamic affinity for bonding with the lighter silicate minerals that make up the mantle and crust. It behaved like a bubble of air trapped in a cooling sponge. Instead of sinking, it was carried upward by the convective currents of the molten earth. As the crust solidified, the sodium was concentrated in the outer shell of the planet, particularly within the igneous rocks like granite and basalt. The transition of sodium from a static mineral in the crust to a dissolved ion in the sea required the intervention of a secondary planetary scale cycle, the interaction of H2O and the atmosphere. As the early Earth cooled and the first rains began to fall, a process of chemical weathering was initiated. Rainwater, which is slightly acidic due to dissolved carbon dioxide, strips the sodium out of the feldspar and other volcanic minerals. To explain the engineering of this on the fingers, the H2O molecules act as a set of molecular crowbars, prying the sodium ions away from their crystalline cages and carrying them into the streams and rivers. Because sodium compounds are highly soluble in water, they do not precipitate out easily. They remain in the flow, eventually reaching the lowest points of the planetary geography, the oceans. For billions of years, the Earth has been functioning as a giant distillation machine. The sun evaporates pure H2O from the surface of the sea, which then falls back onto the land, leaches more sodium from the rocks, and carries it back to the ocean. In the sea, the sodium atoms finally found their most stable and enduring partner, chlorine. This chemical marriage created the sodium chloride, NaCl, that defines the salinity of our planet. This process is so relentless that if the world's oceans were to be evaporated entirely, the resulting sodium-rich salt would form a layer of mineral over 150 feet thick across the entire surface of the planet. We are living on a planet that has effectively vacuumed the sodium out of its mountains and stored it in its basins. This cosmic and geological journey defines the current state of the 11th element as a noble fugitive. It is a material that survived the high-energy birth of the universe and the violent death of a massive star, only to find a home in a liquid archive of planetary history. The sodium ions in a single drop of seawater have remained unchanged for millions of years, maintaining the chemical equilibrium that allows life to exist. The element's presence on Earth is not a uniform distribution, but a concentrated legacy, found in the white salt flats of the Andes, the deep salt domes of the American Midwest, and the tears of every biological organism. The abundance of sodium on Earth, it is the sixth most common element in the crust, is the only reason the complex biological systems of the present were able to emerge. If sodium had been as rare as lithium or as insoluble as titanium, the electrical signaling required for a nervous system would never have found a medium to operate. The planet's salinity is a structural guarantee that ensures the energy of the universe continues to hold its shape in the face of time and entropy. Every gram of sodium extracted from a mine or used in a factory is a fragment of a star that died long ago, repurposed by the Earth's geological plumbing to act as the primary preservative of our world. It is a material that bridges the gap between the high-energy physics of the cosmos and the low-energy stability of a saline world, proving that the most essential components of our reality are the survivors of a long and chaotic journey from the heart of the galaxy to the floor of the sea.
We are effectively living on a warehouse of stellar ash that was swept into the oceans by the rain, providing the salty foundation for everything that would eventually learn to think and breathe. The history of human interaction with the 11th element is a narrative that spans several millennia, characterized by a transition from the ritualistic preservation of the dead to the violent birth of modern electrochemistry. For the vast majority of this timeline, sodium existed as an invisible ghost, a substance that dictated the economy and biology of civilizations, while remaining entirely hidden behind the chemical masks of salts and minerals. The ancient world did not possess the concept of a metal that could be extracted from white powder. Instead, they viewed the compounds of sodium as fundamental forces of nature, capable of arresting the process of biological decay and serving as the primary medium of global trade.
The eventual unmasking of the metal in the early 19th century was not merely a laboratory success, but a philosophical earthquake that dismantled the last remnants of alchemical mysticism and proved that the most mundane materials in the human environment were actually repositories of concentrated electrical energy. The earliest large-scale engineering of sodium compounds occurred along the banks of the Nile, where the ancient Egyptians harvested a naturally occurring mineral known as natron. This substance, a complex mixture of sodium carbonate and sodium bicarbonate, was the primary technological tool used in the process of mummification. To understand the efficacy of natron, one must examine the causal chain of biological preservation at the molecular level. When a biological body is exposed to the atmosphere, the H2O within the tissues provides the necessary medium for microbial enzymes to begin the process of putrefaction. Natron functions as a multi-stage chemical barrier.
First, its high salinity creates an osmotic pressure gradient that physically pulls H2O molecules out of the cellular structures, much like a dry sponge drawing moisture from a damp cloth. Second, the alkaline nature of the sodium carbonate raises the pH of the tissues to a level that is lethal to the bacteria responsible for decay. Furthermore, the sodium ions interact with the fatty acids in the body's adipose tissue, initiating a slow process of saponification, essentially turning a portion of the body's fats into a stable, waxy soap. This chemical taming of the flesh allowed the Egyptians to create monuments of human biology that have remained structurally intact for over 3,000 years. Throughout the Middle Ages and into the Renaissance, the social and economic weight of sodium was concentrated in the form of sodium chloride, or common salt. In an era before mechanical refrigeration, salt was the only available technology for the long-term storage of nutrients. The ability of sodium to stabilize proteins and prevent the growth of pathogens made it the white gold of the era, a material so essential for survival that it served as a primary form of currency. The etymological link between the word salary and the Latin salarium, the salt allowance given to Roman soldiers, is a linguistic fossil of this dependency. However, despite its ubiquity, the true identity of sodium remained a mystery. The leading scientific minds of the 18th century categorized soda and potash as fixed alkalis, substances they believed to be elementary earths that could not be further decomposed. They saw the white powders as the final destination of matter, unaware that these stable minerals were actually the exhaust of a high-energy metallic reaction that had occurred in the hearts of stars billions of years prior. The transition from this state of ignorance to the era of elemental discovery was facilitated by the invention of the first reliable source of continuous electricity, the voltaic pile. Developed by Alessandro Volta in 1800, this device provided the scientific community with a subatomic hammer, capable of striking at the bonds that held molecules together. In 1807, at the Royal Institution in London, the chemist Humphrey Davy utilized this technology to perform a series of experiments that would redefine the human understanding of matter. Davy was a researcher characterized by a restless, high-energy intellectual style, and he approached the problem of the fixed alkalis with a degree of physical aggression that mirrored the reactivity of the elements he sought to find. The engineering of Davy's 1807 experiment was a masterpiece of thermal and electrical management.
He realized that as long as the sodium was dissolved in H2O, the electricity would simply break down the water into hydrogen and oxygen. To reach the metal, he had to eliminate the H2O entirely. He took a sample of caustic soda, sodium hydroxide, and heated it until it reached a molten state. This required a temperature of approximately 604 degrees Fahrenheit. In this liquid state, the sodium and oxygen atoms were no longer locked in a rigid crystalline structure. They were mobile, though still bound by their electrical attraction. Davy then submerged 2 platinum electrodes into the molten liquid and connected them to a massive battery consisting of 250 pairs of copper and zinc plates. The causal chain of electrolysis is a process of forced electronic migration. When the circuit was closed, the battery began to pump a relentless stream of electrons into the negative electrode, the cathode. At the same time, the positive electrode, the anode, began to strip electrons away from the surrounding molecules. Inside the molten soda, the positively charged sodium ions were attracted to the cathode. As they struck the metal surface, they were forced to accept an electron, a process known as chemical reduction. For the first time in the history of the Earth, the sodium ions were being reverted to their pure, high-energy metallic state. According to historical accounts by his assistant, the moment the current began to flow, small, shimmering globules of a silver-white material began to appear on the surface of the electrode. These droplets possessed a high metallic luster, looking like liquid mercury, but they were so buoyant that they floated on the surface of the caustic melt. The drama of the moment was heightened by the metal's inherent instability. As soon as the droplets encountered the oxygen in the laboratory air, they began to catch fire and explode, releasing a brilliant yellow light. Davy, overwhelmed by the realization that he had unlocked a secret of the universe, was reported to have jumped and danced around the room in a state of ecstatic excitement. He had proven that the earths of the alchemists were not fundamental building blocks, but were cages for a new class of elements, the alkali metals. This discovery marked the definitive end of the alchemical era and the beginning of the chemical revolution. It proved that chemical affinity, the force that holds the world together, is fundamentally electrical in nature. Sodium was the primary witness in this trial. The fact that a stable white powder could be split into a psychopathic metal and a corrosive gas if using salt, or oxygen if using soda, demonstrated that matter is a state of energy management. The world was forced to accept that the most peaceful substances under their feet were actually composed of materials that were too nervous to exist in the open air. The naming of the element followed a similarly logical path. Davy proposed the name sodium based on its source in soda, which itself was derived from the Arabic suad, a term for a salt-rich plant used in glassmaking. However, in the Germanic and Slavic scientific traditions, the element was named natrium, reflecting its ancient heritage in the Egyptian natron. This dual nomenclature persists today in the chemical symbol Na, a permanent record of the transition from the burial chambers of the pharaohs to the high-voltage wires of the 19th century laboratory. The historical impact of the isolation of sodium extended immediately into the industrial sector.
Although the pure metal was too reactive for structural use, the understanding of its properties allowed for the development of new manufacturing processes. It led to the Solvay process, a high-efficiency method for producing sodium carbonate on a massive scale. This chemical, in turn, was the essential ingredient for the production of glass, soap, and paper. The 19th century was literally cleaned and housed by the industrial management of sodium compounds. The ability to manufacture cheap soap through the reaction of sodium fats provided a level of public hygiene that did more to extend the human lifespan than almost any medical intervention of the time. To look at the historical drama of sodium is to see a material that has governed human progress from the shadows. We moved from an intuitive use of its preservation powers in 3000 BC to a precise electrical extraction in 1807. The element did not change. Its 11 protons and its single, restless outer electron remained identical throughout the ages. What changed was the human capacity to provide the energy required to untrap it. Sodium taught us that the world is not what it appears to be on the surface, that the white grain of salt is a thermodynamic ceasefire, and that behind every stable crystal lies a history of cosmic fire and subatomic tension. The psychopath of the periodic table was the very material that forced us to realize that we live in an electrical universe, where the difference between a peaceful kitchen and a laboratory explosion is nothing more than the movement of a single electron. Sodium was the catalyst that turned the human species from observers of matter into architects of the atom, proving that the most profound secrets are often hidden in the most common of places, waiting for a spark of curiosity and a surge of current to bring them into the light.
The functionality of a high-technology society is supported by the silent, rhythmic operation of the 11th element, which serves as the primary conductor for both the artificial light of our cities and the biological electricity of our thoughts. While the previous historical narratives of sodium focused on its role as a solid mineral or a reactive metal, the contemporary hidden engine of the element is characterized by its movement as an ion and a vapor. Sodium is the fundamental regulator of the global infrastructure and the human nervous system, performing a role so essential that its removal would result in the immediate cessation of all complex biological activity and the darkening of the world's primary transportation networks. This transition from a quote 50 to an quote 51 is a masterclass in the utilization of atomic scale energy gradients to perform macroscopic work. The most visible manifestation of sodium's modern utility is observed in the distinctive, monochromatic orange glow that illuminates thousands of miles of highways and industrial districts every night. The high-pressure sodium, HPS lamp, is an engineering achievement that relies on the specific quantum mechanical properties of sodium vapor. Inside the translucent ceramic tube of an HPS lamp, made of synthetic sapphire to resist the corrosive nature of the metal, a small amount of solid sodium is heated until it transitions into a gaseous state. When an electrical current is passed through this vapor, the electrons of the sodium atoms are quote, 52 into higher energy states. To explain the physics of this light on the fingers, a sodium atom is like a musical instrument that can only play one very specific, powerful note. When the excited electrons fall back to their ground state, they release photons at a wavelength of exactly 589 nanometers. This is the quote 53 and it accounts for nearly all the light the lamp produces. Because this frequency sits almost exactly at the peak of the human eye's sensitivity, sodium vapor lamps are among the most efficient lighting technologies ever devised. They convert electricity into visible light with a percentage of efficiency that dwarfs standard incandescent bulbs. Furthermore, because the orange light is monochromatic, it does not scatter as easily in fog or rain as white light does,
providing a level of contrast and safety that allows the global logistics network to operate 24 hours a day. The warm, almost supernatural hue of the nocturnal city is not an aesthetic choice, but a rigorous application of spectral physics designed to maximize visibility while minimizing energy consumption. However, a far more critical and sophisticated __54__ operates within the microscopic boundaries of every living cell. This is the sodium-potassium pump, a specialized protein mechanism that acts as the primary battery charger for the human body. To understand the necessity of this biological machine, one must view the cell not as a static bag of fluid, but as a pressurized electrical circuit. The brain, the heart, and the muscles all function by sending high-speed electrical signals. These signals are not the flow of electrons through a wire, but the high-speed movement of sodium ions, Na+, through the cell membrane. The engineering of a nerve impulse is a masterpiece of electrochemical management. At rest, the sodium-potassium pump uses a significant portion of the body's total energy, approximately 25% of every calorie consumed, to physically push sodium ions out of the cell while pulling potassium ions in. To explain this on the fingers, the pump acts like a mechanical bailer on a leaking ship, constantly working to keep the ____55_ on the outside. This creates a state of extreme tension, where the sodium ions are ___56_ on the exterior, desperate to rush back in to achieve equilibrium. When a nerve fires, specialized ___57_ in the membranes snap open. The sodium ions surge into the cell like water through a breached dam, creating a sudden shift in electrical charge. This wave of charge is the thought, the heartbeat, or the muscle contraction. The second the signal passes, the pump resumes its work, resetting the ___58_ for the next pulse. We are, in a very real sense, biological machines, powered by the ___59_ potential of sodium, managed at the scale of individual atoms to ensure that the spark of life remains controlled and rhythmic. In the realm of advanced industrial engineering, sodium acts as the ___60_ within the cooling systems of fast breeder nuclear reactors. To generate massive quantities of carbon-free electricity, these reactors operate at temperatures and power densities that would cause a standard H2O cooling system to flash into steam and lose its ability to move heat. Liquid sodium is the engineering solution to this thermal bottleneck. Because sodium has a wide liquid range, remaining a fluid from 208 degrees Fahrenheit to 1621 degrees Fahrenheit, it can absorb an immense amount of heat without boiling, or requiring the massive, high-pressure containment vessels that water-cooled reactors demand. Liquid sodium possesses a thermal conductivity that is approximately 100 times higher than that of H2O. This allows it to act like a high-speed thermal sponge, soaking up the intense energy of the nuclear core and carrying it to the steam generators with unparalleled efficiency. Furthermore, because sodium is a metal, it can be moved using electromagnetic pumps that have no moving parts, relying on the magnetic properties of the liquid metal itself to drive the flow. This eliminates the risk of mechanical seal failures and increases the reliability of the system. In this capacity, the __61_ metal that once exploded in a laboratory beaker is repurposed as a calm silver river of heat, providing the stable environment necessary for the next generation of high-energy physics to power our civilization. The chemical industry also utilizes sodium as a ___62_
in the production of modern detergents and pharmaceuticals. Sodium hydroxide, NaOH, often referred to as caustic soda, is the primary agent used in the process of saponification. To explain this on the fingers, a fat molecule is like a long tangled ball of yarn that H2O cannot grip. The sodium in the caustic soda strikes these molecules, 63 them into smaller pieces that have a water-loving, 64, and an oil-loving, 65. This is the birth of soap. Without the aggressive chemical intervention of sodium, the global standard of hygiene that has doubled the human life expectancy over the last century would be impossible. Sodium is the element that __66 water. How to wash away the oils and pathogens of the industrial world. As the world transitions toward a renewable energy economy, sodium is once again emerging as a primary protagonist through the development of sodium-ion batteries. While the early 21st century was dominated by lithium, the scarcity and high cost of that element have created a technological ceiling. Sodium, which is chemically similar to lithium, but nearly 1,000 times more abundant and found in every ocean, offers a path to truly mass-scale energy storage. The engineering challenge of a sodium battery is the size of the ion. A sodium ion is larger than a lithium ion, meaning it requires more, 67, to move within the battery's electrodes. However, new research into, 68, anodes made from renewable materials like agricultural waste has provided the microscopic _69 needed for the larger sodium ions to park and release their charge. These batteries are safer, cheaper, and capable of operating at lower temperatures than their lithium counterparts. We are standing on the threshold of a _70 where the same element that builds the salt flats of the Earth will act as the massive buffer for the global electrical grid, storing the sun's energy during the day to power the orange-lit highways of the night. Finally, sodium acts as the silent architect of our visual world, through its role in the manufacturing of glass. Every window in a skyscraper and every screen on a smartphone contains, 71. In the furnace, sodium carbonate, soda ash, is added to the silica sand to act as a, 72. To explain this on the fingers, pure silica has a melting point of over 3,100 degrees Fahrenheit, which is incredibly difficult to maintain on an industrial scale. The addition of sodium lowers this melting point to a more manageable 1,800 degrees Fahrenheit. The sodium atoms act like a chemical lubricant, sliding between the rigid bonds of the sand and allowing the structure to liquefy and flow. Sodium is the reason glass is a transparent and affordable commodity, rather than a rare laboratory luxury. The _73 of sodium is therefore a story of total integration. We live within the transparent walls it helps build. We travel under the orange light it provides. We think and move because of the electrical gradients it maintains in our cells. And we clean our world with the chemicals it enables. It is a material that performs its duties through a state of __74_, utilizing its high-energy valence electron to drive the most essential processes of life and industry. We do not see the sodium vapor in the lamp or the ions in our nerves, yet our entire modern existence is built upon these invisible, high-speed transactions. Sodium is the __75_ that has been successfully drafted into the service of order, proving that even the most volatile and __76_ elements can be harnessed to provide the highest level of stability and convenience, provided they are managed with absolute engineering rigor. Without this restless element, the complex, high-speed reality of the 21st century would lose its charge, returning to a state of biological and industrial silence. Sodium is the spark in our thoughts and the glow in our street, the elemental bridge between the high-energy fire of the stars and the saline peace of the home. The ultimate legacy of the 11th element is not recorded in the ephemeral data of digital servers or the crumbling architecture of human cities, but is inscribed into the very spectrum of the light that the planet Earth broadcasts into the interstellar void. Sodium is the element of the __quote _77 __, a substance that possesses a unique and overwhelming ability to interact with electromagnetic radiation in a way that remains detectable across the vast distances of the galaxy. Long after the biological signals of the human species have faded and the radio waves of our era have been diluted by the cosmic background, the physical presence of sodium will remain the primary chemical marker of our world's history. This permanence is a consequence of the element's indestructible atomic core and its role as the terminal resident of the global hydrologic cycle. Through the lens of deep time, sodium functions as a planetary scale witness, recording the transition from a watery, living world to a desolate, crystalline desert, and eventually returning to the stellar furnaces from which it was forged billions of years ago. The mechanism of this __quote_78__ is rooted in the physics of spectral absorption and emission, specifically the phenomenon of the Fraunhofer D-lines. To explain this on the fingers, every element in the universe possesses a unique __quote_79__ of light that it absorbs or emits based on the energy levels of its electrons. Because sodium has a single, highly reactive outer electron, the energy required to __quote_80__ this electron is remarkably specific. When the broad spectrum of white light from the sun passes through the Earth's atmosphere, the sodium atoms present in the air act as microscopic filters, selectively __quote_81__ photons with a wavelength of exactly 589 nanometers. This leaves a distinct, dark gap in the rainbow of light that reflects off the Earth and travels into space. For an observer located in a distant solar system, utilizing a high-resolution spectroscope, this gap, a sharp double line in the yellow-orange portion of the spectrum, would be the most prominent chemical signature of our planet. It is a beacon that announces the presence of a saline, mineral-rich world with a degree of clarity that no other element can provide. This atmospheric signature is maintained by a persistent __quote_82__, located approximately 60 miles above the Earth's surface in the region known as the mesosphere. This layer is not a leftover from the planet's formation, but is a dynamic result of a continuous celestial bombardment. Every day, thousands of microscopic meteorites and grains of cosmic dust collide with the Earth's upper atmosphere at speeds exceeding 25,000 miles per hour. As these particles incinerate due to friction, they undergo a process called ablation, where their constituent minerals are vaporized into an atomic mist. Because these meteorites are remnants of the early solar nebula, they are rich in sodium. This creates a self-replenishing reservoir of neutral sodium atoms that drift at the edge of space. During the night, these atoms participate in a phenomenon called airglow, where they release the energy absorbed from the sun during the day, emitting a faint, orange light that is invisible to the naked eye but easily detected by sensitive instruments. In modern astronomy,
This sodium layer is utilized as a laser guide star. Scientists fire high-powered orange lasers into the sky to excite these atoms, creating an artificial glowing star at a fixed altitude.
By measuring how the light from this artificial star is distorted by atmospheric turbulence, telescopes can adjust their mirrors in real time to achieve a level of clarity that rivals space-based observatories. In this capacity, sodium is the element that allows humanity to correct the vision of the planet, using a layer of stellar ash to see more deeply into the heart of the universe. The long-term geological destiny of sodium is tied to the inevitable thermal evolution of the Sun. In approximately 1 billion years, the Sun's luminosity will increase by roughly 10%, raising the Earth's average surface temperature to a point where the global hydrologic cycle begins to break down. As the temperature climbs toward 150 degrees Fahrenheit, the rate of evaporation from the oceans will exceed the rate of precipitation. This initiates a process of planetary-scale distillation. The H2O will be stripped of its hydrogen by ultraviolet radiation and lost to space, but the sodium will remain. Because sodium salts, primarily sodium chloride, NaCl, are not volatile, they cannot evaporate or escape the planet's gravity. As the oceans vanish, the sodium that has accumulated in the sea for 4 billion years will precipitate out of the liquid, settling into massive, blindingly white plains of crystalline salt. These __quote_87__ will be the tombstones of the marine world. A single location like the Salar de Uyuni in Bolivia, which currently contains approximately 10 billion tons of salt, is merely a miniature prototype of this future Earth. The entire surface of the planet will be transformed into a vast, white battery of stored mineral energy. These salt deserts will be the most durable records of our world's biological past. Within the crystal lattice of halite, microscopic pockets of ancient H2O, known as fluid inclusions, can remain sealed and pressurized for hundreds of millions of years. These tiny time capsules can trap atmospheric gases, mineral signatures, and even dormant microorganisms, preserving a high-fidelity sample of the 21st century environment within a solid-state mineral vault that is immune to the passage of eons. The chemical indestructibility of sodium ensures that it will be the last material to represent the complexity of Earth as the solar system approaches its final act. In approximately 5 billion years, the Sun will exhaust its hydrogen fuel and expand into a red giant. As the solar atmosphere reaches out to consume the inner planets, the Earth's surface temperature will rise toward 2,000 degrees Fahrenheit. At this threshold, the salt deserts will finally meet an environment that can overcome their structural resolve. The massive plains of sodium chloride will liquefy, creating glowing orange oceans of molten salt. As the heat intensifies, the sodium will eventually reach its boiling point of 1,621 degrees Fahrenheit and vaporize into an atomic gas. To explain this on the fingers, the stellar shrapnel that arrived on the early Earth and spent eons in our oceans and our nerves will finally be uncaged. The sodium atoms will be returned to the interstellar medium, drifting through the vacuum once more as the same stable, heavy particles they were when they were first forged in a neon-burning star billions of years earlier. This return to the void is the ultimate cosmic recycling. Because sodium is a stable element, those same 11 protons that once facilitated the firing of a neuron in a human brain or provided the glow of a highway lamp will continue to exist, drifting through the galaxy as part of the raw material for the next generation of stars and planets. The story of sodium is therefore a narrative of profound and honest continuity. It is the element that reminds us that the universe is a closed system where nothing is truly lost, only transformed. We have merely borrowed this nervous and explosive metal for a brief historical second, using its unique electrical potential to drive our thoughts and its spectral clarity to light our way.
Sodium is the element that taught us that the world is not what it appears to be, that a peaceful grain of salt is a thermodynamic truce between a psychopathic metal and a suffocating gas. It is the material that bridges the gap between the high-energy fire of a supernova and the saline peace of a human tear. In the final accounting of the cosmos, sodium is the most visible element in our inventory because it is the only one that leaves a permanent, luminous signature in the sky. It is the yellow thread that runs through the entire fabric of reality, from the first 3 minutes of a star's middle age to the final evaporation of a planet's oceans. We are biological manifestations of a saline environment, walking extensions of an ancient sea that learned to carry the 11th element within us to power our consciousness. Every thought we have is enabled by the high-speed movement of sodium ions, and every night we navigate is lit by the excitation of sodium vapor. When the last human has spoken and the last machine has rusted, the sodium will still be there, waiting in the white silence of the salt flats, serving as the ultimate biographer of a world that was once vibrant and full of liquid H2O. It is the most chestnut, honest witness, because its signature is written in the light itself, a permanent orange signal that will remain legible to the universe long after the Earth has been reduced to dust. Sodium is the eternal sentry, a shimmering bridge between the high-energy past of the stars and the cold, stable future of an empty planet, proving that the most influential forces in our world are often those that are the most difficult to contain and the most brilliant when set free. Our high-tech civilization is merely a brief resting stop for a material that was born in fire and is destined to return to it, carrying the memory of our existence in the vibration of a single yellow-orange photon.